Hello, everyone. So I'm Magnus. I'm senior members of the programming languages team here in Edinburgh. I think most of you know me already, to those who don't. So today I'm going to talk a bit about effect handlers in Cangjie, what they are, how we did them, and what we want to do with them. So it's a fairly high-level overview of what we've been doing. Okay. So what are effect handlers? That wasn't a rhetorical question. I was hoping someone could tell me what they are. What are they? They're things that handle effects, which is fine. It's not really very useful. They this describes effect handlers or algebraic effects. Or are they? According to Edinburgh Futures, effect handlers provide a computation construct that allows programmers to define, customize, and compose more expressive and flexible computer programs. Futures, but I think maybe you said this, Sam. Yes. They are an algebraic effect handler is basically an exception that carries a continuation, which is not unreasonable, I don't think. And I say that they're basically an exception that you can resume. A lot of other people say this as well. There's a formal definition, there's a sort of practical definition that people have when they use them. I think a lot of the time it's a means of separating an effect from the implementation of the handling of it, and which is quite a subtle description, but I think when you actually use them, it becomes clear what the benefits are. The other thing, of course, is that you can use them to avoid using monad transformer stacks, but I don't think that's a particularly helpful way of describing them. Okay, so effects in Cangjie. So I said effect handler is just an exception you can resume. So when implementing effects in Cangjie, we decided to take that and basically run with it. So we expanded the try-catch syntax for exceptions in Cangjie, and then we added the try-catch finally became try-catch handle finally. So we now have a handle keyword in the language. Oops, no. It's analogous to catch. Rather than catch an exception, you handle a command type. Any effect has to implement this command type. But unlike exceptions, you now have this resumption object as well. This is the continuation of the point where you performed the effect. So when you can handle this, do some sort of error correction or handling, and then you can resume this resumption later and jump back to the point where the effect performs. So this function read file performs an effect. When you resume, you'll jump back into exactly where the effect was performed. So yeah, new keywords added to the language, perform and resume, and new types, the command type, and the handle keyword, of course. The resolution for these handlers is basically the same as it is for exceptions. You dynamically traverse up the stack looking for an appropriately typed handler for your effect. So let's look at this example above in more detail. So we have this read file function, and if it reads a file, it takes a file name as a string, and if the file does not exist, we perform an effect. Rather than throw an exception, we perform an effect saying we haven't found this file. And we don't specify what we do about this, we leave it up to the handler to decide. So in this case, we run the function, this file food.txt doesn't exist, and what happens here, control here, because this file doesn't exist, jumps to this handler here with the parameter containing the resumption and the effect here. We then resume with the default value back here. So this returns, so this is an extra syntax we've added here. So you can just resuming, jump transfers control, but you can pass a parameter as well. So when you resume, the perform will return with a value. in this case, a default file name. So rather than just handling an exception and having to bail out, we can just transfer control back here with an appropriate default value. Is everyone happy with that, with the control flow? Oops. Control flow here. So we perform an effect, we jump out to the handler. We retain this continuation here, and then when we resume, we jump back to this position here and carry on. Yeah. Okay. So there's some design challenges from doing this, that particularly with extending the try, catch, finally syntax, there's a bunch of issues that come up with doing this. Particularly, we have a finally clause, which is supposed to happen once, and it's supposed to happen regardless of what you do. So what happens if basically you store the resumption? You perform an effect here, we handle it, but we store the resumption and we leave this block, and then later on at some point we resume back in here. What happens here? When does this finally block run? Immediately after we come off the handle block? That's what would happen if it was an exception. Or does it run when we resume back in here and come off this try block here? That would also happen in the exception cases. So does it potentially resume never? The finally block, does it potentially run never? Does it potentially run twice? In this case, the person who wrote this program is expecting it to run once and only once, but severe consequences say if it doesn't. So how do we handle this case? And also, how do we deal with resuming into a function that's potentially returned already? What happens in that case? So the way we dealt with this is we split our implementation of effects into two separate strands, essentially. We have the deferred handlers, which is the full effects implementation with storing of continuations and resuming them later. And this is proper effect handlers. So what we have here is that we basically allow the resumption to be potentially never used. In this case, finally will possibly never run. And that's just the design we specified. That was a compromise we had to make. So this is I'll come to how we mitigate that in some ways. So this finally block will potentially never run. It will run, it's specified when the try block. It won't run when we fall off this handle. The resumption is stored. If we resume the resumption, the finally block will be run when we resume back in here and fall off the end of the try block. At that point, we will run the finally. And we thought this was the best way of handling this situation. And resumptions can be resumed arbitrarily. They also now have a second type parameter. So when you resume, so what happens, like when I said a function that is potentially returned, or what happens if like this function isn't this, the way this is implemented is these are closures containing the code, the continuation. So what happens if I resume in here, and this is in a different stack that's gone, and then or a function is already returned, and I finish this block, where does it go? Well, what we specified here is that resume actually will return in this case. So when we resume in here, when we reach the end of this try block, we run the finally, and then resume will return back to this position here with the specified type, which in this case is the unit. So, but you can define your resumption type and your effect so that you can return arbitrary values at this point as well. And of course, resumptions can only be at this point in time resumed once. If you try to do it, it's not statically enforced, but it will be a runtime error if you try to resume resumption twice. Okay. So the flip side to this is immediate handlers. So this is almost essentially the default case in Sandy. This is how you're how everybody's encouraged to use effects, and if you really need to leak a resumption, use it, you would use deferred handlers, and then at that point on your head be it if you mess with the finally semantics. In this case, you must resume after handling the effect. It's statically enforced, and the syntax is slightly different here. You have no explicit resumption parameter here. It's entirely implicit. You resume with no without specifying the parameter of without specifying the explicit resumption. You can also still specify a value to be returned when perform returns here, but otherwise, yeah, it's just explicit. You must do it on all code paths. This is statically enforced. At this point, what you have is something very much, well, essentially is resumable exceptions. Well, you can do quite a lot with this. Just having the sort of dynamic resolution and handling of an effect of a handler function, and then resuming back into where you were, it gives you a very strong inversion of control, and you can do a lot with this just using the dynamic binding. And because what we've done here, this allows very extreme optimizations on the original effect handlers code. This is much faster than the full effects. These effect handling and resumptions basically become plain function calls. Okay, so how does it work? So our implementation relies on stack switching, and by this I mean the full implementation of deferred handlers. As Stephen mentioned, Cangjie also has lightweight multiplexed concurrency using the spawn function, and we reuse the existing infrastructure for this for implementing our effect handlers. So each future or thread spawned in Cangjie that has a full is stackable. It has a full stack. I've used that to sort of save and restore the stacks when we switch the handlers. So how does it work for deferred handlers? So what happens is we have the normal function stack in main here. When we enter the try block, this code is run on a new stack. Essentially, we spawn a new thread, and that thread runs the code in the block here. Now, when we perform, that thread yields, if we go back to the main stack to run the handler function, and that handler function is run on the main thread, or the parent thread, to be precise. And when we resume, control is returned back to the try block thread, and the thread is restarted at that point. Unfortunately, when we implemented this, the Cangjie runtime does not give explicit support for yielding and stopping, pausing threads, and resuming them later, and so on. So we had to. Everything is managed by a very heavyweight scheduler. So there's a lot of sort of hacking involved, trying to persuade it to allow us to do this, and it works pretty well in the end, but we had to add some extra runtime functions and so on to do this. Anyway, so when you resume, you go back into the thread stack that was running in the try block, and when we finish, the thread terminates and control yields back to the parent. And this works when you nest these as well. So when you nest a try inside a try, it spawns another thread, and so on and so forth down to until as far as you want to go. And it just when you perform an effect, it finds the handler function, it finds the thread that's running in the context, and control is transferred to that thread and back again. Now, for immediate handlers, it's much simpler. This is basically everything's on the same stack, and we basically desugar everything into a plain function call. So the try block just becomes a lambda, and we enter that and call it. The handle block is another lambda. We resolve it, and then we just immediately call the handler. When we resume, that's just the handle block returning control back to the function which called it, which is the perform call. So this gives us a very significant performance improvement compared to doing this. There's no surprising behavior in terms of like finally blocks, throwing exceptions or whatnot, or resuming into, it doesn't allow you to resume into functions which are not valid or have to do with return value of resuming, for example. And this covers, as I said, this covers many different use cases. So you don't lose too much from doing this. Okay. Should be a title here. I don't know where it's gone. Anyway, how does we? I've talked about resolving the handlers. So how does that work? This is common to both the deferred and immediate implementations. So how do we, when we perform an effect, how do we resolve the handler that we want to run? So when we create a try block, regardless of whether we spawn a thread or call a lambda, we create a node in a linked list, and each node contains another list of the command types that's handled by the associated handlers in that try block. And it also has a lambda for each handler function or a closure. And we keep track of the current scope by keeping which position in this tree we are. And when we perform, we traverse up the linked list of the linked list until we find the matching handler of that for that type we just performed. Just like the same, very similar to handling exceptions. And we then set the current scope to that point in the tree for the purposes of, if that handler happens to perform a function, perform an effect, we start the resolution from that point. Oh, there's my title. Okay. So when we perform an effect, so this is performs other effect. We first search this node in the block. We traverse upwards. We find it. So then we run the handler function, and that's now our scope. Okay, does anyone have any questions on the implementation side of things, or the design, or anything? Sam?
So you can imagine if you're having to traverse up this stack repeatedly,
Yes.
just accessing some dynamic variable, that might be quite expensive. Is there any potential for collaboration?
Yes.
To the same place?
We've tried a couple of things for this. One of them was building a very highly optimized data structure that made this traversal simple and much more algorithmically better, but on some micro benchmarks, it showed some improvement, particularly when you have very deeply nested try blocks. However, was in real life applications, it didn't really show much difference at all. Similarly, we did something with memoizing or caching the handler, and again, didn't show much in as good a result in practical applications as it is in the benchmarks. However, I think we want these sorts of things to be enabled as like potential user specifiable optimizations, I think, rather than just something we apply globally, because I think there will be sometimes when these things will work. I have a feeling that there's a way you can, a better way to optimize this traversal. I think that sometimes there's like some static information you can use as well. It should make it, there are cases when you can statically optimize this, and there's some other things you can do, but I haven't been able to sort of like nail it down yet. I have a feeling there are a lot more you could do with this, but still something ongoing. That isn't where the bottlenecks are. So, okay, so we have built this nice effect handling system, but not an effect system, just the effect handlers themselves. And what can we now do with that now we've got it? I said earlier, one of the main uses of effects is to avoid monad transformer stacks. Obviously, that doesn't really apply to Cangjie because you have side effects when you want them. The other big thing is custom schedulers. You want to use effects to implement lightweight concurrency, and then if you're spawning a thread, for example, as an effect, you can use the handlers to write your own custom schedulers. We can do things like aspect-oriented programming, where we specify cross-cutting concerns and use handlers to specify how we handle them and implement them across different parts of the application. The other big one is dependency injection, and you get this for free with the dynamic binding with the handler resolution in effect handlers. I've used the phrase resumable exceptions quite a lot, so obviously error handling is something that's quite a useful application of this. And then again, tying into what Steve was talking about UI and so on, reactive programming using so React.js use something akin to effect handlers to handle impure side effects in their reactive UI functions. You could also use effects to implement such a reactive system where changing a state performs an effect and then use handlers to propagate that and nest that. So there are many things we can do, and I'll give a little whistle-stop tour of things we've looked at and tried. Okay. So caching and memoization using effects is something we can do. So consider the Fibonacci function. I suppose everyone's familiar with the Fibonacci function. So we want to optimize this using caching because it's something trivially easy to do, and we want to do this using effects. So we have our existing Fibonacci function, and we've decided we want to go for an object-oriented approach here. So we have our default Fibonacci function, which just does it normally. We have our effect type here, which implements the command type, and we call it the Fibonacci effect. And one thing I didn't touch on our wrapper function, which performs the Fibonacci effect with a number parameter here, and that just implements it. And something I didn't touch on is we also have support in Cangjie for default handlers. So if an effect is unhandled, if you don't specify a handler for it, that will result in an exception for unhandled or runtime error for unhandled effect. However, if the effect you're performing has this method defined, or default impl here, if the effect is unhandled, this will be run at the top level, and this always resumes. So in this case, if this effect is unhandled, we will just calculate a normal Fibonacci function and then return the answer to it. So that's what we're doing here. Okay, so when we run this, it will just calculate Fibonacci each time fully expensively. What we can then do is we can use a handler to cache these cache the Fibonacci results and reuse them later. So here we have this function which takes another function as an argument, and what this does is takes a function and runs it in the context of this handler. And what this handler does, we create a hash map to use the cache, and every time if we have a cache miss, if we have a miss in the cache, we reperform the effect, and then we put the result in the cache after we've got the computation, and then return the result. And if we find that if there's a cache hit, we just return the cache value, and then we resume with the result value. And you'll note this is not specific to the Fibonacci effect we defined before. This could be used with this is a generic function we can use as any effect type that returns some sort of value. And you can apply this handler to anything, and it will, as long as there's another handler or a default handler for that type, it will return a computed value, and this thing will cache it. So this sort of demonstrates that you can compose different effects together or different handlers, and how you can reuse this sort of stuff across your code base. So when we do this, this is your normal Fibonacci call here. This is extremely slow. When we run our Fibonacci function within this handler, you get a you cache each result, but because this loop is out here, you're throwing away this cache each time and reinstalling it and reinstalling the handler. However, you can just hoist this out here, and then you get to reuse this cache between calls of Fibonacci, and you get a very this is linear time now. It computes this very quickly. And this sort of defining a handler as a function, first-class function that takes another function, is kind of an idiom that we've adopted in Cangjie. So, and we have this nice syntax for trailing closures, kind of similar to Swift. So this makes good use of that. So what if you want to cache the recursive calls? How much time do I have left? That's okay. You can also extend this to cache like the recursive calls itself, and not have to reuse and not have to sort of cache between calls. So you can modify the effect type to take an initial parameter. It doesn't take the initial parameter directly. You specify an extra parameter, and what happens here? The handler gets a bit more complicated. You reperform. This relies on the explicit assumptions to do this. I forgot how this works. Sorry. Anyway, it does work. It does make it much faster. This, and this is more memorization rather than caching, really. But each recursive call is much faster again. So we've gone from. So now we can do rather than what was it? So before this was identical to this behavior in terms of performance, but now we have changed the handler slightly, and we end up with this. This is equally as performant as having to look within it. Okay. Talk briefly about incremental computing. We can use effects to automatically build dependency graphs, and this can support incremental or reactive programming. We create a cell, and every time we touch this cell, it performs an effect. Reading from it performs a get effect. Writing to it performs a set effect. And only contain an ID to sort of identify it to the scheduler. And what I don't really have time to go into details of how it actually works, but basically by recursively installing a handler when we are writing to the effect, anytime that is read within the writing and so on, you use the recursive handlers to build a dependency graph, and then when something changes, you can just incrementally update everything that relies on that cell. So in this case, we create some cells. We create another cell sum, which is dependent on these two. This performs effects each time, but we've added some nice syntactic sugar here. This is not real syntax. This is basically a DSL within the language. And each time we update one of these cells, these functions will fire. So the sum will be recalculated, and then this will be printed out. These functions will print out, so that the sum will be recalculated, and you'll see that these values have changed each time. Okay, I'll be very brief now, we're running out of time. So I mentioned dependency injection as well. We can use effects with two different kinds of dependency injection. We can identify a function. So we have logging here, for example. So this function performs a log, and then we specify, and the user specifies how they want to handle the logging effect themselves. So they can decide they want to just append to a log, they can have it print out, they can have it send it an email or whatever, and just change the handler to decide how that works. We can also do classical object resolution and instantiation using dependency injection as well, using lazy code or what have you. So we use effects to perform the lookup of where to find the object, and then that gives us an object that we can then just use as if it was an ordinary, like any other object. So this is more akin to dependency injection in terms of things like, what's the one we use in Java? The DI frameworks and stuff. Neo. Spring has it? Yeah. Neo4j? No, that's something else. That's database. Yeah, okay, never mind. This just illustrates the sort of things you can do with effects. Okay. And you want to use this where you have creating an object might be expensive, but it's not long-lived. So like if you have a database connection, then you use this sort of system to provide a database connection, and where each time we close it, but then we're actually reusing the same one without having to reconnect and so on, just by using this system for dependency injection. Okay, what are we continuing to do with this in Edinburgh and Huawei as a whole? So we're continuing to investigate applications of effects, how we can use them to improve productivity and developer experience and so on, and also how we can use them to do optimizations and develop new frameworks and so on. We're also looking at multi-core effects, like how do we handle, so I said briefly that our threads are multiplexed on real threads. How do we handle effects that are handled in different threads? How do we perform one real physical thread and handle another? So that's something we're going to actively start to look at. Effect systems. None of this is really encoded at the type system beyond the checking that the parameters to resumptions and commands match up. We'd like to have some sort of way of tracking which effects a function would call, but that is, we haven't looked too much at that. Also maybe expanding that to handle like what exceptions a function might throw, maybe checked exceptions, but not, well, obviously we do it better than Java did it. And finally, we're exploring other angles as well. I think we're thinking about asynchronous effects possibly as well. That'd be something nice to have. Effects that come from out with the system, like if you have a UI, what happens when the callback fires and performs an effect, because that comes from out with the system. There's not necessarily any handler installed to handle that. How do we deal with that? Yeah, and also how do we integrate this with the existing concurrency systems? How do we integrate it with actors and so on? There's various things we're looking at and what we can do with effects. Okay, that's the end of my talk. I hope I didn't run too far over time. Thank you very much.